What is ARCHER2? Well, it's the new UK National Supercomputer Service managed by the Research Councils and EPCC. It's housed, operated, and supported by us, EPCC. I'll explain what we are in a second. And it's a Cray machine. Well, I should actually say it's an HPE machine. Apologies, Cray, part of HPE, Hewlett Packard Enterprises. But as part of running that service, we provide training. The computational science and engineering team provides training, and about 60 days per year. I say at various locations, but of course it's been all online due to current situation. The full system launched very, very recently, and so I don't actually have a picture of the full system. This is an artist's impression of it, I'm afraid. That is actually the original, the interim system, the 4-cabinet system. That's quite nice to show you how much wiring and such like there is in the back of these machines for the interconnects and such like. There's another machine, Cirrus, but we're not using that for this course. What is EPCC? Well, we're the closest thing the UK has to National Supercomputer Centre. We've been around since 1990, originally the Edinburgh Parallel Computing Centre, hence our name. We're a self-funding centre of excellence at the University of Edinburgh, and we've been running national parallel systems for almost 30 years now. We now have over 100 full-time. The first machine was a Cray T3D, coincidentally a Cray machine back in the early 90s. We have over 100 full-time staff. We do a range of academic and commercial projects, and we do postgraduate teaching and HPC training as well. And the reason I put this up is, you know, if after this course you say, oh, that was really interesting, but I'd like to work with EPCC to do some more, you know, collaboratively in some sense, get in contact if you want. We do commercial projects, but also in terms of research projects, our staff just work like research assistants. So a lot of EPCC staff work on joint research proposals with other academic research groups in the UK and historically in Europe, but of course the States and Europe is like in question at the moment. You know, if this was a face-to-face course, you might be in Edinburgh. You're not, you're sitting at home, but I thought I'd put a picture of Edinburgh up. It's a shame we can't use the physical training facilities at the moment, but that's the way things are. There's ARCHER2 resources, but you won't need, hopefully all the exercises are pre-packaged. Who am I? I should explain. I'm David Henty. I'm in charge of education and training at EPCC. That covers our MSc, our PRACE Training Centre, and this course is part of the PRACE programme, but also courses on the ARCHER2 training programme. And my interest in HPC are kind of parallel program accelerators, but mainly performance, which includes I/O. Other resources, you won't really need many other resources, but please fill in the feedback form at the end. You'll be sent a link at the end of the course. We take feedback very seriously. Good feedback is great. We can go back to EPSRC and say how wonderful we are, but also poor feedback is also taken very seriously. It allows us to improve the courses, and the feedback can be done anonymously. We also run an MSc in high performance computing. It may not be interesting to you, but you might know people who are interested. I'll plug that a bit. These are some of our students from a few years ago. It's available both on campus and online. And we do have an MSc in HPC and HPC with data science, which is run as part of the University of Edinburgh. We also have a supercomputing MOOC developed under PRACE. There's the URL there. Again, probably not interesting for you. You'll be too advanced for this, but maybe interesting for people you know. It's very much conceptual, no programming course, but hopefully a useful conceptual introduction. It now runs in a self-study mode, but it's open and people are still doing the course and then going through the materials. During the course, you have personal accounts and you'll get access to the machine for up to about a month afterwards. We'll close 2 weeks after access ends, so please take copies of all your work. If you do have work, this isn't a programming course, you may not have things, you may not actually have programs there, but the main point is the materials, the slides and the exercises will continue to be available from the ARCHER2 website, so don't worry about losing access to the slides. We're also recording the lectures here, but any of your own work you will need to take away within the next month or so. Again, security of the room isn't an issue for this course. There is a code of conduct. You should maybe have a look at it. It's just general stuff. We expect people to be collaborative and realize that people come from a lot of different backgrounds, a lot of different levels of experience. So try to be supportive. And if there are any issues, you can report them. There are funding calls where we support software development on ARCHER2, and there's the URL there. The ARCHER2 hardware software setup, very briefly. We're not going to be talking about this a lot because we're talking about the I/O. I'll talk about the disks later on. But there's almost 6,000 nodes, each with 128 CPU cores. There's more than 750,000 CPU cores in this system. It is quite astonishing, I have to say. You have two file systems. This one in the lectures, but we will be working in /work. This is the parallel file system, and you must run all jobs from /work. During the course, we have reserved queues for fast turnaround. Outside of the course, you'll just have to use the normal queues if you want to do the exercises in your own time. This course is also part of the PRACE European program, a European project which we're a member of. There are 26 members, and EPCC represents the UK. It's still ongoing despite the UK status in Europe. And there, as part of that, PRACE funded 10 training centres, PRACE training centres. We are one of them. There are 10, and these training centres provide free courses across the whole of Europe. So if you're interested, you can look at that training, prace.ri.eu, for other training courses. PRACE funds delivery for these courses, I said please fill in the feedback form. So I hope you enjoy the course. I really would say please ask questions. I have lectures, there are exercises, but I think it really is important to, I would rather spend the time answering questions that people want to hear the answers to, rather than just going through slides that aren't maybe, which I hope they're interesting, but they might not be what you want to know. So please ask questions. Probably we can use audio if you need, but initially it's easiest if you ask them in chat, and I will get a notification. So what I will do now is I will just show you where the material, you should know this of course, but let's see where the material is. There we are. So this is the ARCHER2 homepage, which you all know. If we go to training, we have the upcoming training. This is the course you're on at the moment, Efficient Parallel on ARCHER2. If you can see, it's a PRACE course. If you go to this link here, we have the timetable, but the main point is that we have the course material. So this is really the page I expect you to be looking at now. It's a fairly blank GitHub page, but hopefully it has all the information you need. Now, I would say this is the first time I've run this course. I'll explain later. So I apologize. Now, we will finish on time, but I think that some of the early lectures are longer than I expected, and the later ones may be shorter. So we may not stick exactly to the timetable. I apologize for that. But there will be ample time for practicals, and there will be breaks and such like. So we will stick to the breaks. We will have breaks when the breaks are indicated, but the practicals might shift slightly depending on how the timing goes. I apologize for that. You'll see here that all the lectures should be linked in here, so that should be give you a, please give me issues. Please tell me if there are problems with these links, and also the exercise sheet will come back to here. And so hopefully this is your home page for today, and you should be able to see all that stuff there. So what I wanted to do now, though, actually was I would just be useful to get a basic idea of the people who are attending. So it would be good if, give me a second, it's going to be slightly, if people could go to a particular URL. So it would be really good if I could just I want to run a quick quiz to basically to get an idea of what people's backgrounds are and what you want to learn from this course. So sorry about this. Two seconds. So if you could go, I'll give you the URL in a second. So in a few, I will just start. If you could in a few seconds go to this URL, which I'm about to show, and we're going to do a quick quiz, which is really just about, if you could go to that. So this, okay, there we are. And room name is HPC Quiz. I will now start that quiz. So you should, so because people managed to, I don't, okay, people are joining now. Okay, so if people could log on, it's just a very, thanks, Kevin, I was about to type that in, but we got quite a few people. So if people could go to that URL, which Kevin has helpfully put in, because of course you can't cut and paste from my screen, of course, and put in HPC Quiz, and you should, oops. So what I will do is I will stop sharing that. I've run a parallel I/O course for many, many years, but it's previously been focused on how to develop MPI-IO for parallel I/O. I think I've realized that people are more interested, as I definitely saw in the answers there, in just in general how parallel I/O works. So that's why I've developed the course again. I redeveloped the course to focus more on the generics. So what I'm going to do is just give a lecture here talking about the challenges of parallel I/O at a conceptual level. Again, please ask questions, and I do apologize if there are any typos or mistakes in the slides. I said this is the first time I've run the course, and so so what I'll cover here is why I/O is difficult, why parallel I/O is even worse, the kind of straightforward solutions people use in parallel, what should you be trying to achieve, and then a very brief overview of how MPI-IO views parallel I/O. The reason why MPI-IO is useful to understand, but we're not going to actually learn how to program, but understand it conceptually, is it's a useful library which is used by a reasonable number of applications, but also it has the same approach as other libraries like HDF5 conceptually. But more importantly, libraries like HDF5, NetCDF, and other things like ADIOS I'll mention later on, eventually call MPI-IO. And so if you understand how MPI-IO works and how to make MPI-IO go fast, even if you're not programming in MPI-IO, your HDF5 library is 99% sure going to be calling MPI-IO. So actually, that's why, so understanding MPI-IO performance and how it works is very useful, because it basically is the bottom layer for other I/O libraries. But why is I/O hard? I/O is nasty. You have this nice virtualized process memory model, but then this data in memory has to physically appear on some external device on your disk. Files are very restrictive compared to data arrays. A data array, you can do random access. To do random access in a file requires seeking, and that's very inefficient. And you may have to remap your program data to get it into a linear access in a file. There's lots of system-specific options to I/O calls. There's lots of formats: text, binary, big little endian, fortran unformatted, which is the bane of our lives, HDF5, NetCDF. The hardware is very complicated. We have things called RAID disks. There's lots of layers of caching. It may be cached on disk in memory. I always think I/O is the HPC equivalent of printing. You get your new laptop, you set it up, you're up and running in 10 minutes, and then you try and get your printer to work because you have to get the data, your document to appear on a physical device. It's a nightmare. What I would say here is I/O systems are very complicated, so I'm going to try and give you general concepts here, but it's very hard to say definitive things. And I think an analogy I came up with this morning is a bit like driving a car. You can learn to drive a car. You can go out into the roads and drive your car. You can write a program which calls parallel I/O calls. But just because you can drive a car doesn't mean you can predict congestion. You know, you can drive a car, but it's incredibly difficult to predict congestion on motorways. That depends on a huge number of things: what the roads are like, how many other users there are, drivers. That's the same with I/O. So it's really important to understand the general concepts and then do experiments to find out what works best in your situation. So here's my canonical example. Okay, if we have a 4x4 array. Okay, so we've got in C double x44 or 4 times the same thing. I wrote this in C because the pseudo C because the actual benchmark is 4 times, and I just initialize it, and I've opened a file pointer, and I do double x4. I write it x size of double. There's 16 entries to a file pointer. So this is the serial data. It's a 4x4 array. And we of course know that arrays are, or even 2D arrays are just basically linear arrays of 16 elements. Now I've colored these, you can ignore that for the moment. But what happens is when I write this data, the 2D array goes into the file and it has elements 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That would be the way I do parallel I/O in serial. Sorry, that's how I would do serial I/O. I have a 4x4 array. I open the file in C with a file pointer. I f-write all 16 entries, and then I'll close it, and I get the data on file mapped from the memory into file. Okay, so that's the canonical example I'm going to think about, writing a 4x4 array. Now, of course, in reality, the arrays are much bigger, but I'm just using a 4x4 array as an example. So that's my canonical example. In parallel, imagine we're on 4 processes. You've distributed this array, and that's what the colors are. Imagine we now distribute this array in a 2D way across 4 processes. So the first process owns that data, the second that data, the third that data, the fourth that data. So it's important to note now that we have 4 processes, 1, 2, 3, 4, and each one just has a 2x2 array. So my definition is now double x22, but I have 4 processes. Then I insert some magic parallel I/O call, which will do the same thing. But the important point here is, even with this very, very, very simple example, which the 2x2 array, a 4x4 array on 4 processes, the I/O pattern is surprisingly complicated. The data from this process appears here and here, and this, you can see we're getting this quite complicated pattern. So it's very important to realize that it isn't true that the first quarter of the file is yellow, the second quarter is blue, the third quarter is green, and the fourth quarter is red. Because we've distributed the data in this 2D decomposition, we get quite a complicated, even with this almost trivial example, we get quite a complicated I/O structure. So you can see that parallel I/O is going to have challenges because the data from each process isn't a single contiguous block of the file, it's scattered into the file. So the data from process 4 goes here and here. Now we end up with the same file. The file here will be identical to the previous file, but I've numbered the data elements 1, 2, 3, 4 because each process only has 4 elements. So is that clear? That's my serial I/O. This is what I want to achieve in parallel, but it is surprisingly complicated to do. Okay, so that even this simple example, and I'll come back to this example again and again as an exemplar to try and illustrate what's going on. Okay, the naive solution, okay, is, well, what some people say is, well, why don't I just open the file, okay, and everyone opens the same file, and they write the data, then they just write the data where it needs to go. Each process just writes into the same file. All 4 processes open the same file and write the data where it needs to go. So we do XX22, we have a pointer, we all open the same file, okay, it's an MPI program, and then we all seek to some process-specific offset, which I'd have to compute and write. Now, this will not work in general, because for two reasons. First of all, multiple processes writing the same file is problematic, okay? Now, actually, I should say I concentrate on write here for two reasons. Write is more complicated than read, because you have the possibility of clashing, but also most MPI parallel programs write more often than they read. I think an order of magnitude. You know, if you're doing a climate model, a weather simulation, you read in the weather today, you run for 10 days, and you dump the weather every day. You tend to write a lot more than you read, okay? So writing is harder, and typically, typical parallel programs, big simulation programs, typically write about much more than they read. And also performance will be poor. You actually require many cycles of seek, write, seek, write. You know, we'd have to, this blue process would have to seek to here, write, then skip. It would just be a nightmare. The performance will be appalling. But even more importantly, when I say problematic, this is not guaranteed to work. And I'll come back to that. Why is parallel I/O harder? We cannot have multiple processes writing to a single file. Unix/Linux cannot cope with this, okay? Unix is not a parallel file system, okay? So, you know, it cannot cope with this in general, because the data is cached in units of disk blocks, which are typically about 4K and not coherent. I'll illustrate that in the next slide. It's not even sufficient to have processes writing distinct parts of the file. You might say, I don't see the problem here, because each process, each process is writing to a different section of the file. Well, we'll see that's not going to work. Even reading can be difficult, okay? Unix was not designed with parallelism in mind. If you have 124,024, or we saw 750,000 processes opening a file, that can overload the file system. The file system just may not be able to cope with that. Unix file systems were not designed to be opened, have files opened 750,000 times. As we've seen, the data is distributed across different processes. Processes do not in general own contiguous chunks of the file, so you have this kind of, you know, scattered data product. You can't easily do linear writes. You have to do scattered writes, and actually even more complicated. Your local data may have halos. You know, in fact, your local data might not look like this. You might have tend to have junk data in parallel programs, often halo data all around the outside. So parallel I/O does become quite hard. Why simultaneous access doesn't in general work is because of the way that now I/O is very slow. Writing to disks is slow, and the way that you make things which are slow faster is you don't do them. So writing to memory is slow. Why isn't your laptop cripplingly slow? Because when you write to memory, you don't really write to memory. You write to cache. And that's the same for disk I/O. Okay? When you write to disk, it doesn't write to disk. It will try and write to memory, which is quicker, and then maybe later on drain the data to disk. It's very complicated. But you make I/O fast by not actually writing to disks until you really have to. And so there's a lot of caching goes on. So imagine we have a file, and it happens to be split into 3 disk blocks. Now, a disk block we're not really going to come back to this, but fundamentally, when you read a file, the minimum amount you can read is a disk block. When you think you're reading 1 byte, the operating system actually reads a whole block, which is probably about 4K or might be bigger, but it's going to read a whole. That's the minimum quantum of which you can do I/O transactions to the disk. So even if you read a byte, you'll get a disk block. So process 1 has a disk cache, which is probably a memory cache, okay? Process 2 has its own disk cache, which will be, now remember, again, in a parallel machine, process 1 and process 2 could be on different machines, on different nodes. And what's going to happen is we're going to say, well, process 1 is going to read some data. It's going to read that data. So it only wants this amount, but it caches the whole disk block 1 and disk block 2. Process 2 wants to read this data, but it overlaps. It actually takes the whole disk block 1 and disk. That's fine. Okay, not a problem. And then process 1 reads what it wants into its memory, and process 2 reads what it wants into its memory. Then process 1 updates the data, and process 2 updates the data, and then they write. Now, of course, the operating system says, well, David wants to write to disk. That's really slow. I'll just write to disk cache for the moment. That's much quicker. And then his program can carry on. So I update that my disk cache, and process 2 updates its disk cache. Sometime in the future, when you're later on in the day, or when your program finishes, or you shut down, it's going to say, I'm going to actually have to write this data to disk. And so it flushes the disk caches. But it doesn't, but that mechanism does not code for two processes opening the same file. Process 1 thinks it's the only person that's altered this file. Process 2 thinks it's the only process that's altered this file. And so process 1 flushes its disk cache, then process 2 flushes its disk cache, and you get garbage here. Because these caches are not kept coherent, because by default, a standard Unix file system doesn't understand parallelism. So it doesn't really matter if you didn't understand the details there, but the important point is it's both very slow and not guaranteed to work, to have lots of processes just using standard Unix IO or Fortran IO, opening the same file and writing to it. It's not a good thing to do, and it may not work. Or any quick questions about that? So the standard thing that people do is independent IO. It's also called file per process. Each process opens its own data file, writes its local data. Now, this is very simple to implement. It's a nightmare to cope with in practice. You end up with thousands of files, and that often requires a lot of pre and post processing. Also, the data format depends on the number of processes. If I run on 8 processes, I get 8 files. If I run on 16 processes, I get 16 files. You get a completely different output from the serial code. It's a very common solution, but I find it philosophically wrong. I think that parallel computing should get the same result, but faster. And I mean that both computationally and in terms of IO. So a lot of people do this, but it is not an elegant solution, and it does have its own problems. So what you do here is, okay, each process has its own array x22. Each one opens its own local file, so you have to create a local file name. Let's put the process number in there. So you have data1.dat, data2.dat, data3.dat, and data4.dat. So when I write this data, I get 4 data files, each with the local data. That's fine. That's very quick, relatively simple, but it's a nightmare, because when my program finishes, I have 4 files, 750,000 files. How do I cope with them? I end up doing lots of pre and post processing to stitch them all back together again. And so this is not an elegant solution. Now, we will cover how to make this solution tractable, maybe improve its performance, make things a bit easier for yourself. But it is not, I don't think it's an ideal solution, but it may be the only one you have. So I will cover it to some extent. This is what we really want to achieve. We want to have the parallel data to produce the same file as we would have in serial, where the data goes to the place that the position of the data in the file doesn't depend on how the decomposition works or how many processes you're running on. Naive solution number 3 is called controller IO. So we send all the data to or from a single controller process. So we maybe scatter or gather from or to other processes, say to rank 0, and then we write or read a single file. So I haven't actually got an example for this, but you can see what you do. You nominate a controller process, and conventionally we pick rank 0. If you're doing writing, you basically pull all the data, gather it all into rank 0, and rank 0 just does serial IO, but you get the same. So the advantage is the output is the same as the serial program, because what you would do is you reconstruct this entire array on a single rank 0, and then write it out in the normal serial manner. The issues are we quickly run out of memory on the controller. It's very unlikely that one process can store the entire data, so you have to write out in small chunks, which gets more complicated. But the main point here is the performance is very poor. That we only have only a single process is ever writing. This is a serial solution, and you get no benefit from a parallel file system. Now, this is not obvious at the moment. When after the next lecture, hopefully you will see that although this solution gives you so you have a potentially fast but inelegant solution, which is individual file per process. You have a maybe more elegant, maybe but slow solution, which is controller IO. And again, a lot of programs use these two relatively naive approaches. But again, controller I/O has real issues in terms of memory and performance. So what do we need? We want a way to do parallel I/O properly, and we want the I/O system to deal with all the system specifics. We don't want to have to worry about the details of the ARCHER2 file system. We want a single format. We already have, and we want the file we produce to be the same as the serial file. All files should have the same format as the serial file. The entry is stored according to position of the global array. Now, a number of libraries exist, and we will consider it MPI-IO first because it illustrates the concepts of our I/O libraries, but it's also the building block for most of them, so it's useful to understand. I'll only go over it very briefly. Previously, this whole course spent a whole day on MPI-IO. I'm really just going to illustrate it, and we'll play around with it in terms of a benchmark. So the important point about parallel I/O is how does the I/O system need? What does the I/O system need to know about the data? If you're going to use a parallel I/O library, you're going to need to tell it where the data goes, how the local arrays should be stitched together to form the file. But actually, the mapping from the local data to the global file is only in the mind of the programmer. Okay, the computer, the programmer, doesn't know that we think the process is arranged in a 2D grid. If you write an MPI program which has data like this, this is where I get a problem. Okay. Process 1 has a 2x2 array. Process 2 has a 2x2 array. The fact that your MPI program imagines these to be subsections of a large distributed array stitched together in this 2D format is in your mind. It's in the it's not explicit, and so you're going to have to tell the I/O library, look, when I write this data, process 2 is going to own this bit, this bit. You have to describe how the local data which you own maps into the global file. And that is the additional step. This is the problem in animations. It's hard to go forward and backwards. That's the additional step. How do we describe the data layout to the I/O system? Different libraries will have different ways of doing it. HDF5 will have one way, MPI has another way. But this is the crucial step in all parallel I/O. You have to tell the I/O library what portions of the global file each process owns. And that is an additional step which then allows the I/O library to stitch the data together correctly and give you the right answer. So again, as I said, you may have this view that you have a 4x4 array distributed across 4 processes, but the computer is actually a picture of a very old computer, Hector, just thinks there's 4 processes, each with 4 data items. Okay, you need that information is in your head. It doesn't. Your program doesn't really know that. So the way that these things work, how do you describe, and this is really thinking about an MPIO, think of the file as a large array. Forget that the I/O actually goes to disk, okay? So imagine we are recreating a single large array on a controller process. And what we do is we say, imagine we had a large 4x4 array. I'm process 4, I own the top right-hand corner. And then once the I/O system knows that, the I/O system, the library you're using, be it HDF5 or MPIO or something else, must create this array and save to disk without running out of memory, never actually creating the entire array, i.e. not doing naive controller I/O, but by doing a small number of large I/O operations. We'll see later on that what a good I/O system does is it merges the data together, so it does a small number of large writes rather than a large number of small writes. And you want it to use any parallel features. If there's multiple I/O nodes, and we'll talk about this later, or manage all this coherency stuff between file blocks. But basically, the I/O library has to do a whole bunch of stuff, but hopefully that will be hidden from you. And so you should never implement this yourself. You should use an I/O library. So the MPIO approach, which I'm going to cover in the 3rd lecture, MPI-IO is part of the MPI standard. MPI came out in the early 90s. They'd hoped to address I/O in the first instance, but it turned out to be a bit problematic, so they delegated it to MPI-2, which came out in the mid-90s. The MPI-IO approach is that each process needs to describe what subsection of the global array it holds, and it does that using MPI data types. So what we do in MPI-IO is what we want to say is, okay, we've got this 2D distributed array. Process 3 needs to tell the I/O library that the global array is a 4x4. The file represents a large global array, which is 4 by 4, but each process needs to say, look, I own this bottom right-hand corner here. And MPI has a mechanism called derived data types. Now, these derived data types were not introduced for this purpose. They are introduced to allow you to send subset. Imagine this is an this is an array I have in an MPI program. If I do an MPI send, I cannot easily send this bottom right-hand corner because it's not 4 contiguous elements. An MPI send operation has a pointer, a count, and a data type. Okay, I can't do that here because 9, 10, there's a gap here. MPI has a system of MPI derived data types, which allows you to specify, amongst other things, non-contiguous array sections. So you can define, and we'll cover very briefly how this is done, a subarray, and you can send it as a single item. You can say, I want to send one subarray. And MPI-IO hijacks that process. It uses that MPI derived data type mechanism to allow each process to specify what subsection the global array owns. Now, we don't need to understand that in detail, but the important part is any IO library will have a phase where you describe what data each process owns, and MPI-IO uses MPI-derived data types to do that. Now, MPI-IO is usually the lowest level. You may never call it directly. Higher level libraries exist. HDF5, NetCDF is something used in the climate community. ADIOS, I should have ADIOS 2 there, is a new library which I don't have a lot of experience with, but I know some people are using. It's very flexible. It can write using MPI-IO, HDF5, or its own formats. But the approach is always the same. There'll be some way of describing what portions of the file each process owns, or portions of the file. And these libraries typically use MPI-IO to do their reads and writes, which is why I think understanding MPI-IO, at least conceptually, is useful. Summary, okay. Parallel I/O is difficult in theory and in practice. MPI-IO provides a high-level abstraction where the user describes the global data layout using derived data types. MPI-IO hides all the system-specific file system details, but hopefully takes advantage of them for performance. But we'll see that does require some work from you, and we'll investigate that when we run our benchmark. More flexible formats like NetCDF and HDF5 exist, and ADIOS, but they gain their performance by layering on top of MPI-IO. So they basically use MPI-IO because to do their actual I/O, so that they're layered on top of it. And the user requires a good understanding of derived data if you're going to use MPI-IO, but that's not quite so essential here. So that's my lecture. Does anyone have any questions? So hopefully just check now, I've restarted. Can you hear me and see the slides okay? Just useful if someone would confirm that. Great. Okay, fine. So we've talked about the conceptual challenges of parallel I/O, but now we're going to talk about parallel file systems. So this is previously these were all one lecture. I've tried to pull them apart. One of the good things now, though, is that Lustre, which we use on ARCHER2 and on ARCHER and other systems, is pretty universal now. So though I will talk about parallel file systems in general, I will also tend to concentrate a bit on Lustre because it is pretty universal. So I'll cover what parallel file systems are. I'll quickly go on to the Lustre file system. I'll talk about striping, which is the fundamental way that parallel file systems achieve performance and take advantage of parallel hardware. I'll talk about some simple Lustre commands, and then discuss briefly what the bottlenecks might be in the I/O, excuse me, and what we'll do in the exercise is start to explore what some of these bottlenecks might be. So What's a parallel computer? Well, a parallel computer is nothing particularly special hardware-wise, at least from the processor. It's constructed of many standard processors, each not particularly fast. I mean, the CPU cores in ARCHER2 are no faster and possibly slower than the CPU cores in your laptop. But the important point is your laptop has 2 or 4 of them. Archer has 750,000 of them. So the performance comes from using many processors at once, although the processors themselves are not particularly special. And it requires manual distribution of the data and calculation across processors. It's up to you. People, I mean, in the early days of parallel computing, people were surprised that they took their program, their Fortran C program, ran it on a parallel computer, and it went no faster. It might have gone slower. No, you have to do something special. You have to distribute the data and the calculation across processors using MPI. Parallel file systems are constructed of many standard disks, each not particularly fast. The performance comes from reading or writing to many disks at once. And that requires many clients to read or write to different disks. And your fundamental building block when you're writing an MPI program on multiple processes, it turns out in parallel I/O systems, each node appears as a separate I/O client. So Archer has 6,000 nodes. Each of those is actually a separate computer with a boring name. I can't remember what they're called now. Node 1, node 2, up to node 6,000. The parallel file system thinks of ARCHER2 as 6,000 individual machines all connected to the same file system. So each node, which is each of ARCHER2, appears as a separate I/O client. But the important point is that data from a single file can be striped across many disks, and we'll come back to that. That's the way that you achieve better performance for a single, better performance for I/O to a single file. You also achieve better performance with the parallel file system for writing to multiple small files, and I'll explain how that works. But if you want to get better performance for I/O to a single file, it comes from striping. I'll talk about that later on. But parallel file systems are very complicated. They have lots of disks and lots of stuff going on. But to you, okay, we'll see that a single file can be striped across many disks, actually across many Unix file systems. But you don't want to know about that. It must appear as a single file system to the user, although actually it's lots and lots of different file systems stitched together. Typically, we have a single metadata server, the MDS, which is the thing which has the global view of the file system. And so the metadata server stores the information on, what your files are, what they're called, where they are, and where they're stored, and then they're physically stored across multiple disks later down. But it's important to understand that you have this database, this metadata server, and that can become important in terms of performance. So here's a conceptual diagram of a parallel file system, Lustre. We have the application processor running on compute nodes, process 0, process 1, process 2, process n-1, each with their own memory. We then have some high-speed network, which on ARCHER2 is this slingshot network. We have a metadata server, which we also have separate nodes. We have I/O processors. There are actually separate I/O service nodes which handle the I/O, which sit between your program and the disks. And these I/O calls them a metadata server, which actually has a disk called a metadata target, but I only ever normally talk about metadata servers. There are actually object storage servers, which could have multiple object storage targets. Now, this is quite complicated, but it turns out that I think the most important things to talk about are user processes and nodes, the metadata server, but these are the physical disks. These are the RAID device. These are the physical disks. The object storage targets are the physical disks. So the OSTs, object storage targets, are the most important things. The fact that they're grouped together in servers is not particularly important. So the fact we have a metadata server and lots of object storage targets, which are the physical disks. So when you write data, you have to contact the metadata server to say, where is my data stored? It'll say, it's stored on this, and then you will write data to those disks. So I have, looks relatively complicated, but I personally have a more simple view of how it works. So I don't actually have pictures of the ARCHER2 storage system because it's so new. These are pictures from Archer, but they illustrate, the numbers are different, they illustrate the point. On Archer, the object storage servers was called stable storage units. Sorry, apologies. We had these boxes which had two object storage servers, each of which had 4 object storage targets. So each unit had 4 object storage targets. Now, again, I don't think this hierarchy is relatively transparent. So the important point, I think, is that you have lots. You have lots of object storage targets, which I will call disks. Now, they're not really disks. Okay, the object storage targets are actually RAID devices which have 10 disks, 8 plus 2, where the data is striped across 8 disks, and you have 2 for redundancy and disaster recovery. You have parity bits and all this kind of things. So the object storage targets aren't technically disks, but I will call them disks. They're disk units, they're disk arrays. So I will think of them as a single unit. So I will talk about the object, but actually it's quite a nice picture. Multiple SSUs are combined to form a storage. So this actually has 1, 2, 3, 4, 5, 6 storage racks, each of which had 8 OSTs. So that's 48 OSTs, each of which has 480 physical disks in it. Now, the setup on Archer is different, but we do have a very large number of physical disks in these systems, and potentially a very high storage capacity and storage bandwidth. So my terminology is that Lustre has these many different levels of virtualizations. So one object storage server has multiple object storage targets, and a single OST has many physical disks in a RAID array, redundant array of individual disks. I can't remember what RAID stands for. But the way I think about it, I refer to the following parts of Lustre. The metadata server, MDS, the database that contains information on e.g. where a file is actually stored. And the object storage target, these are the physical devices that store your data. I may also call this a disk, although it contains multiple hard drives. You can't access the individual hard drives individually, so I think of it as a disk unit. I think of it as a disk. The MDS and the OSTs are what you, the user, actually interacts with. So that's why I think they're the most important things. So you should think of, I would think of a parallel file system as being one database, the metadata server, and lots of, we'll come back to how many, disks or object storage targets. So what does the ARCHER2 hardware have? Well, we have 3 separate /work file systems, and an individual project or consortium is designed to different partitions to share the load. So I don't know if you're using the ARCHER2 course account, which is in project TA048, that will have a /work file system on one of work 1, work 2, or work 3. I don't know which one it is. We'll be able to find out, I guess. Each of these work file systems has 12 OSTs and 1 MDS. Okay. And why do we have multiple file systems? We could have one MDS covering all 36 OS. So if ARCHER2 physically has 36 object storage targets, 36 OST storage devices, why split them up into 3 separate ones? Well, it's because a single MDS controls a whole file system. If you had one MDS for 36 OSTs, it might overload it. Okay, so by having 3 file systems, we have 1/3 of the number of users and presumably 1/3 of the number of files on each. We have more MDSs, more metadata servers. So it helps balance the load. Multiple file systems, which are themselves individually smaller, means the MDS is less likely to be overloaded. There's also a file system with solid state SSDs, not spinning disks. It's still to be configured. We expect it to have better latency, i.e. good for small I/O transactions. They may not have better bandwidth. I don't know. I haven't had a chance to look at that yet. Each OS around 3.3 petabytes of storage, which is 13.2 petabytes. Now you might look at the documentation and see that it actually says it has 14.5, but that's because I don't normally get as pedantic as this, but petabyte PIB is in powers of 2. So that's saying that a kilobyte, kibibyte, as the technical term, is 2 to the 10. Now, 2 to the 10 is 1024, which is only a bit bigger than 1,000. But when you get up to these very large numbers, there's a big difference between, I should know what a petabyte is. That'll be a big number. But there's a big difference between the power of 2 and the power of 10 notation by about 10% here. It has 13.2 petabytes or 14.55 petabytes. So it does actually match. I was confused when I worked these numbers out that I couldn't get the right answer. But we have about 13, 14 petabytes of storage. Each file system has 3 or 4 petabytes of storage across 12 OSTs. So the default configuration is each file is stored in a single OST. When you create a file, you do an fopen or a / open. It is assigned to the OST when the file is created. And the Lustre file system will sprinkle multiple files from the same user or multiple files from different users across all available OSTs to balance the load. So basically, if you open 12 files, they could all be on different OSTs, or some might be on. It depends what it decides at runtime, and how the load is going. Each OST is actually a separate Linux file system. So actually, each of these things here is a completely separate Linux file system. You don't see that because the metadata server pulls it all together for you, but actually, each OST is an individual server running its own Linux file system. This is called an unstriped file. Okay. So an unstriped file, or we'll call it striped 1, we'll come back to this, is a file which is just stored on a single disk. So the advantage you get here from having a parallel file system is A, you have multiple disks, which means a lot more storage, and B, different files are stored on different disks, so that might help you with the bandwidth. So reading and writing multiple files from multiple nodes can benefit from multiple OSTs. So if you're using file per process, writing lots of files, you will benefit from the ARCHER2 file system because they will be distributed automatically across different disks. However, access to a single file will not benefit from the parallel nature of the file system because a single file will be stored on a single disk. That's why controller I/O does not benefit from Lustre, because a single file is stored on a single disk. If you do the I/O from a single process, you're not doing parallel I/O. You're just doing normal serial I/O. But file per process, which I'm not a fan of, at least philosophical concept, will benefit from a parallel file system. Now, the way that Lustre helps you with this access to a single file is from data striping. So you can ask or tell Lustre to store a single file across multiple OSTs. So you see a single logical file, big file.dat, but you might say, I want it 1, 2, 3, 4, 5, 6, 7, strange number. I want it to be striped across 7 OSTs. The OST file system divides the file into stripes if requested by the user, and then the stripes are written to from their assigned OST. So this single file is physically stored on lots of different file systems. And this is why you need a metadata server. You say, I want to read the 7,356 byte from my file. Well, you have to take the metadata server, where is it? Oh, okay, it's on that disk there, okay? So that's why you need a metadata server. Each of these is a separate Unix file system. The metadata server makes them look like a single logical file system. So all your normal Unix commands work, although physically it's stored on multiple disks, multiple OSTs. So striping allows multiple I/O processes to access the same file because it increases the bandwidth as you're accessing multiple OSTs. Now, it's important to note this is typically optimized for bandwidth, not for latency. There's a large overhead when for working out where data is and where it's stored. So reading or writing small amounts of data is very inefficient. Okay. Parallel file systems are designed to open a file, write 100 gigabytes, close the file. Okay. Not for seeking around doing little reads and writes all over the place. Okay, but this is called striping. Striping of a file is fixed when it's created and under control of the user, and the fundamental parameters are the number of stripes and the stripe size. So if you ask for a file to be created with with stripe count 4, then what will happen is so that's 4 stripes is not really the correct thing. It's really a count of 4. It's probably well, I'll fix that. Lustre will assign 4 OSTs. You don't know which. Oh yeah, sorry. This is where you'll see that I have some apologies for these typos. I'll fix these. I'll re-upload these after the lecture's finished. So you've said, I'll tell you how this later. I want to create a file. I want to be stored on 4 OSTs. I want a stripe count of 4. Lustre assigns 4 OSTs. Let's call them OST1, OST2, OST3, and OST4. They'll be picked in some way to balance the load. The default stripe size is 1 megabyte. So what happens? The first megabyte of your file is stored on OST1, the second megabyte on OST2, the third on OST3, the fourth on OST4, and the fifth back on OST1. So your file is divided into stripes, and the default stripe size is 1 megabyte, but you can alter that, and those stripes are distributed round robin across the OSTs, and that means a single file is distributed across a whole bunch of OSTs in this round robin fashion. So it's not, if you have a 16 megabyte file, it is not true that the first 4 megabytes are on OST1, the second 4 megabytes on OST2. That's distributed, and that's deliberately done, because if you want to read a large amount of a file, you don't want all that file to be living on a single disk, because you're not benefiting. That's why it's split up. If you say you want to read the first 4 megabytes of the file, that lives on 4 different OSTs, so you get parallel I/O. So that's the reason. But the stripe size is not particularly, well, we can look at it later, but the most important point is the stripe count. I've asked for this file to be stored on 4 OSTs, so it is stored across 4 OSTs. It just happens to be, it's not in chunks, in large chunks, it's in small chunks of the stripe size, which are distributed like a pack of cards in a round robin fashion. Are there any questions about that? Because that's the sort of most fundamental concepts that for serial files, normal Unix, C, C++, Fortran IO, you create a file, it will be stored. If you the default is 1 stripe count 1, which is I'll call unstriped, and each file will live on a single OST, but they can live, different files will live on different OSTs. But for true parallel I/O, you ask for a single file to be stored across multiple OSTs. You have a stripe count bigger than 1, and the distribution is done in these small chunks, like a pack of cards. Are there any questions on that? Okay. So how do we do these? Now, you can set the striping on a directory or a file. I find it much simpler to set the directory. You have a directory called My Output directory. You set the striping on the directory, and every file that's created inherits that striping. So I find that the most sensible thing to do. You can do it on a file-by-file basis, but I don't think that's particularly elegant. So to set the striping on a directory or a file, LFS, Lustre file system, set stripe -c for the count nstripe, and then the directory of the file. Nstripe equals -1 is full striping, so which will be 12 on the ARCHER2 file systems. So again, if you wanted to do full striping, which is probably what you want for really big files, you do LFS step stripe -c -1. To set the stripe size, LFS set stripe -s and say 4 megabytes. We can play about that later. I would just stick with the default, which is 1 megabyte for the moment. This does not alter the striping for existing files. That requires a copy. So if you have a file which is not striped and you want to stripe it, you cannot set the stripe count on it. You have to copy it across. I always use set stripe on directories. All files subsequently created in the directory will have the same striping. I find that the most useful thing to do. To inquire, LFS get stripe on the directory of the file gives you information on how many stripes there are, what OSTs there are, more information than you care to imagine. We'll look at that in an example later on. Parallel IO to a striped file is very complicated in practice. Where in the file does the local data need to be written? Which OSTs are the stripes located on? Are there write conflicts coming from different processes? You need to use a parallel IO library. This is all stuff which is handled for you under the hood. So last, where are the bottlenecks? So this is, is the bottleneck going to be getting the data out of a process? Okay. Is it going to be memory bandwidth? Is the bottleneck going to be data off a node across the high-speed network? Is the bottleneck in the high-speed network? Is the bottleneck in is the bottleneck in how fast you can you write data more quickly from a node or a process than the OSTs can cope with? Well, I say I don't know. I didn't know. I found out very recently on ARCHER2 what it is. If you're an ARCHER user, it is a very different balance. ARCHER had a very large number of OSTs, 50 per file system, but they were quite slow. ARCHER2 has many fewer OSTs, only 12, but they're much faster. So the bottlenecks between ARCHER2 and ARCHER are very different, the limiting factors. Or is it access to the edge which is the limiting factor? Is looking up where a file is the limiting factor? And so it's really important to understand where the bottlenecks are so you can understand what you can improve. So obvious questions are, does the metadata server become overloaded for large numbers of files? If I write 10,000, 100,000 files, does the metadata server just give up? What's the maximum performance for a single OST? Can one process saturate an OST? Can a node saturate an OST? Or is the network the limiting factor? How well do different IO libraries work with Lustre? What are the best stripe count and stripe size settings? So to try and understand all these things, I wrote a simple benchmark several years ago to help investigate Lustre performance characteristics and bottlenecks. And we'll use MPI-IO for the practical examples. It writes a large distributed 3D array of double precision numbers. So it is the my canonical example is a 4x4 array on 4 processes. This is just a generalization to 3D. You'll do a 512 by 512 by 512 array of double precision numbers on, if it was on 8 processes, that would be on a 2x2x2 process grid. Okay, and as I said, that gives you surprisingly complicated I/O patterns in terms of the way that the data meshes together. We'll get it from GitHub. This is all on the exercise sheet, which I'll come to in a minute. It actually came. Now, why is it written in Fortran? Well, I developed this. It wasn't originally a benchmark. A researcher who now I think works for HPE, Anton Sternlicht, had written a program using Fortran coarrays for 3D cellular automata microstructure. So he had these big, very big 3D arrays of double precision numbers, and he wanted to output this data to disk, and he was doing controller I/O, and it was very slow. So I wrote him a library in using MPI-IO to do this for him, and because it was a Fortran program, I wrote it in Fortran. I then copied stuff that my colleague Adrian and Fiona, Reed, who's since left EPCC, did to do HDF5 and NetCDF. I just copied what they'd done as part of a project into the code, and it's been extended a few times since. But all it does is it creates a very large 3D array, distributed, and writes it all to disk in a number of different ways, and we'll investigate how that works. So, summary: a Lustre file system has multiple OSTs. I think of these as being multiple disks. By default, on ARCHER2, each file is stored on a single OST, an unstriped file with a stripe count of 1. But you do get increased performance from files. That could be a single user writing many files, or multiple users each writing a single file. Okay. We'll come back to this, but you're sharing the file system with all the other users. Improving performance for a single file requires striping. It's under the control of the user, and we would expect parallel I/O libraries to take advantage of the striping, and we will see whether that's true or not. So we're kind of on time. What I would say is what we're going to do in the next session after the break is to I'll just share this, the correct thing here, is to do the exercise. I want to do so I seem to be having a problem here. Okay, it's because okay, okay, can you see that? No. Okay, fine. This is what we're going to be about. What's is the parallel IO exercise sheet. So hopefully you can see that, which tells you what we're going to do. Maybe you can. And the first exercise is really just downloading it and running it. You can get the. I would also say that the my bench IO site has a README which gives you some examples and some explanation of what it does. So it may be worth looking at that. It has command line options. They're not very good for two reasons. I'm not a very good programmer, and it's written in Fortran where command line options are slightly quirky. So it is configurable, and the command line options are not particularly user-friendly or robust, but you can do a lot of things. I would recommend you take a break now.